Good afternoon, advanced algebra students. I hope you're doing great. I am actually recording this lesson during Thanksgiving break. We had a teacher work day today on Monday, so I'm using the time to get caught up on some work to plan for you when we get back. I hope that you are resting at home, relaxing, and having a good time. We are going to pick up again in our advanced algebra book the second half of chapter 1. We have covered sections 1.1, 1.2, and 1.3. We are going to pick up today with section 1.5. We did decide as an advanced algebra team this quarter not to teach section 1.4. Section 1.4 is a topic, arithmetic sequences and series, that is often taught in other classes, and so in the interest of streamlining things, we are going to go ahead and pick up with section 1.5. Now, the topic today is solving equations and inequalities by graphing. This method is particularly helpful when you have complicated equations where simple opposite operations will not be sufficient. We have already used opposite operations to solve basic equations quite a bit in this course so far. And so this method is really meant for more complex problems. However, my first example is going to be with a straightforward equation, just so that you can get an idea of the way this method works, and then we will dive into a more appropriate example. The first example is 3x minus 4 equals 2. Now, obviously, this just takes all of about 2 seconds to solve using opposite operations. We would add 4 to get 6, and then divide by 3 and get that x is 2. We're done. So please don't think I'm suggesting that the method I'm going to show you is the most efficient method for solving equations. It is just a method that we can use when we don't have other options. So let's go ahead and do this first example. As I said, it's more of a straightforward problem, but just to get the idea of how things work. What we do is we set y equal to both sides of the original equation. So y equals 3x minus 4 would be our first equation, and then y equals 2 would be the second one. So we have the algebra expression on the left and the algebra expression on the right. Then what we do is we go ahead and graph both equations. So to graph y equals 3x minus 4, we would have a y-intercept of negative 4, and then we would go up 3 and over 1, and then up 3 and over 1 again. And then we would draw a line connecting those points. To graph the line y equals 2, that is just a horizontal line where y is always equal to 2. Now we can see the spot where these 2 points intersect is 2, 2. So first you write y equals to the algebra expression on the left, then you write y equals the algebra expression on the right. After that you graph both. Your answer is the x-coordinate of the point of intersection. In this case, they're both 2, but the reason the answer is 2 is because that is what our x-coordinate is. Now, that was a very straightforward example. Obviously, we would never actually use this method to solve this equation if we were trying to be efficient with our time. But this does come in handy when we have more complicated equations. So let's say we have the opposite of the absolute value of x minus 2 equals negative 1/2 x minus 2. Now the absolute value part of this problem is what complicates things. However, if we use the method that we did here, this really isn't that bad. So our first equation is going to be y equals the opposite of the absolute value of x minus 2. And the second one is going to be y equals negative 1/2 x minus 2. So it's good that we took a moment a week or two ago to review how to graph absolute value functions so that we can do that now. We want to notice that the vertex of this absolute value function is at 2, 0. So we're going to put a dot there. Then we want to notice that the slope of the right-hand side is negative 1. So what that means is I'm going to go over 1 and down 1, and then over 1 and down 1 again to form this part of my absolute value function. And then I'm going to go back 1 and down 1 to do the other branch. So we've graphed the first equation. Now we want to graph the equation y equals -1/2 x minus 2. And I think what I'm going to do is just extend this a little bit more so that I make sure that we don't run out of room. There we go. Okay. So to graph the equation y equals -1/2 x minus 2, obviously I start at a y-intercept of -2. And because my slope is negative, I'm going to go down 1 and over 2. And then I'm going to go down 1 more and over 2 again. And then down 1 more and over 2. And then down 1 more and over 2 again. And then I'm going to connect those dots right there. Now, you can notice that these two equations intersect at 2 points. The first point of intersection is 0, -2. And the second point of intersection is 8, -6. Remember, our solution is always whatever the x-coordinate is of the points of intersection. So our first solution is x equals 0. And our second solution is x equals 8. And if you plug either 0 or 8 back into the original equation, you get a true statement. So we can verify that both of those solutions work. Now, this method can also be used to solve inequalities with complicated expressions as well. So let's take a look at another example. Let's do example number 3. In this problem, we want to solve x plus 3 is greater than 7 minus 3x by graphing. Again, this would not necessarily be something that we would normally solve using graphing, but the purposes of doing so now is to illustrate the method. So again, we set y equal to the left, so y equal to x plus 3. Then we set y equal to the algebra expression on the right, which would be 7 minus 3x. Now what I want to do is graph both of those expressions. And so to graph y equals x plus 3, I'm going to have a y-intercept of 3, and then I'm going to go up 1 over 1 and have that line right there. To graph y equals 7 minus 3x, I'm going to have a y-intercept of 7. 1, 2, 3, 4, 5, 6, 7, right there. And then I'm going to go down 1, 2, 3, and over 1. So I can see that I have that line there. Now, the point of intersection occurs at 1, 4. Again, I want to look at my x-coordinate. The x-coordinate here is 1. Now, because I'm looking, this line right here is the line y equals x plus 3. The question is asking me, when is the value on that line greater than the value of the other line? It would be any time we're past when x is 1. So after x is 1 is when this line has a higher y value than the other line. So our answer here would be when x is greater than 1. All right, good job so far following along. We have 2 more examples to do. Let's do example number 4. We're going to solve x squared minus 4 is greater than 0. Now, we have not gotten into how to graph quadratics yet. So anytime you come across a quadratic, just use a T-chart. You could also use a calculator. I recommend usually graphing values between -4 and +4, and that will cover the vast majority of parabolas for now. So, if we want to set a T-chart up for this, in this particular case, it's going to end up being sufficient to solve for x between -2 and +2. And you can always do that first and see if that gives you enough of the graph. When we do, we get y values of 4, 1, 0, 1, and 4. And then what I would have to do from there is subtract 4. So this would be just y equals x squared. And then if I wanted to do a column for x squared squared minus 4, I would just subtract 4. So this would be 0, and then -3, -4, -3, and 0. It's kind of up to you how you do it. You can plug in these x values for y equals x squared and then subtract 4, or do it all right away. Either way works. When you are done, you end up with these points here. -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. So that is the parabola that you would get. Now, the question is, when are the y values greater than 0? We can see, looking at this graph, that y is greater than 0 when x is less than -2, or when x is greater than +2. So graphing allows us to have a visual of where our y values are positive. Again, where x is less than -2, or where x is greater than +2. All right, let's do one more example. There is another example I had hoped to show you, but it's a little bit complicated to show on a video. So I am actually going to put that example in the stream, and then we are going to go over it during Zoom, because it involves using your calculator, and I'd like to be able to type out the instructions for you. So our last example is example number 5, and whenever I can include anything about a motorcycle in a word problem, you know that I like to. This one says, a motorcycle is 40 miles ahead of a car. The motorcycle travels at an average rate of 40 miles per hour. The car travels at a rate of 60 miles an hour. When will the car be ahead of the motorcycle? So in this particular case, we're going to have x be the number of hours, because it's asking us when something will happen. We're going to have y be the distance, because that's what we're trying to evaluate, how the two distances compare. And the question is, when is the car's distance going to be greater than the motorcycle's distance? So when is the distance of the car greater than the distance of the motorcycle? If we wanted to write an algebra expression for how far the car has traveled, we would just write 60 times x, because the car is going 60 miles an hour for x hours. If we wanted to write an algebra expression for the distance the motorcycle has gone, it would be 40 times x plus 40. The reason that we add that extra 40 on there is because the motorcycle had a 40-mile head start on the car. So we're going to graph y equals 60x. We're also going to graph y equals 40x plus 40. And we want to see, when is y equal to 60x going to be higher on our graph than y equals 40x plus 40. Now, when I graph this, I skip counted by 40s on the y-axis. So I did 40, 80, 120, 160, 200. And then on the x-axis, because this is distance, on the x-axis, I just skip counted by 1. So 1, 2, 3, 4, 5, and 6. All right, so to graph the first expression, y equals 60x, I have a y-intercept of 0, and then I'm going up 60 and over 1. So I'll be at 60 here, and then at 120, at 2 hours, and so on. So that would be that graph there. Technically, I suppose we could continue the line, but time of negative really doesn't apply here. All right, so this is going to be the graph of the car. Now we want to graph a visual for the motorcycle. It's going to start at 40 and then go up 1, over 1, up 1, over 1. We can see that those two lines intersect at the point 2, 120. And remember, our answer is always the x-coordinate. What this means is that after 2 hours, the car is ahead of the motorcycle. You can see that the car, the equation of the line for the car has a higher y value after time is 2. So we would say the car is ahead of the motorcycle after 2 hours. All right, I do have one more example I'm going to put in the stream for you, but for now we're good. Thanks.